A system engineered to lift more than 200 tons to orbit should, by all traditional measures of aerospace design, represent an ultimate statement of stability and certainty. That was the paradox at the core of the Starship V3 operational transition in January 2026. A rocket built larger, wider, and stronger than any orbital vehicle in history, yet still bound by the same unforgiving equations that had already judged every earlier version before it. The announcement marked the moment the system was intended to move from a culture of rapid iteration to one of calculated precision. This shift, however, introduced a subtle vulnerability: the human assumption that the hardest engineering problems had finally been solved. The architecture of V3 was defined by its massive scale, rising 140 meters tall and measuring 9 meters in diameter. Beneath it, the Super Heavy booster carries 33 methane-oxygen Raptor engines, generating a combined sea-level thrust that exceeds 72 meganewtons. The ability to achieve orbit with a payload capacity exceeding 200 tons comes not from a single invention, but from the compound effect of design decisions, including the enlarged tank volume, the stretched V3 variant, and the Raptor's full-flow staged combustion cycles that push chamber pressures beyond 300 bar. Yet every increase in performance necessarily narrowed the tolerance band for stability. The V3 build phase saw significant procedural modifications based on the cumulative data from earlier collapses, fragmentations, and thrust failures. Engineers recalibrated the Raptor architecture, not through reinvention, but through hardening, widening the combustion stability margin by adjusting fuel injector geometry and slightly reducing chamber pressure targets to flatten the risk curve. This demonstrated the critical understanding that the new operational vehicle needed predictability over pure theoretical maximum performance. The environmental judgment on the structure was most severe. Earlier vehicles used thinner stainless steel skins that flexed under shock, and the material flexes more than aluminum under dynamic load. The immense length and diameter of V3 amplified oscillation along the Z-axis, and the structural mass grew unevenly, which meant the rocket grew outward faster than its resistance to bending. This physical reality exposed the limits of a geometry reliant on immense size. Telemetry from the early experimental flights provided critical numerical evidence for systemic risk, identifying vibration traces, temperature spikes, and pressure deviations that became the scaffolding for the V3 redesign. Failures were traced to structural joints misreading in a near-vacuum environment, or propellant imbalance becoming an uncontrollable oscillation inside the tanks, confirming that insufficient margin in one section propagates into collapse somewhere else. This pattern of failure was a black box message from physics. Scaling a rocket cannot be done linearly. Despite the fixes, one vector of risk remains unresolved within the system's operational envelope: the long-term structural fatigue of the V3 architecture under repeated thermal and cryogenic cycles. The booster has not yet proven its endurance to dozens of hot fires and re-entries required for true cost-effective reuse, meaning the final verdict on the core material remains an open question. The core anomaly of the V3 program was the scaling assumption itself. Engineers assumed that increasing tank diameter and wall thickness by the same ratio would maintain stiffness. Records, however, indicate the material response under combined cryogenic temperature and axial load did not remain linear. The physics of large structures punished this oversight. A tank twice as large is often less stiff relative to its own mass, meaning the rocket grew outward faster than its resistance to bending. This curiosity about scaling applied directly to the Raptor engine clusters. With 33 sources of vibration, acoustic load, and thermal flux, microdata inside pressure logs revealed that the wider tanks required thicker internal rings to prevent ovalization under thrust. The complexity meant that engine vibration patterns changed significantly when even one unit deviated from nominal operation, introducing phase interference patterns between the engines. The partial comprehension of the complexity was demonstrated by the changes to the hull material itself. V3 employed a different steel roll pattern and modified alloy composition to resist thermal buckling during re-entry. Even the weld geometry was changed, using wider seams to distribute stress more evenly and reduce the chance of microcracks that had previously propagated under vibration. This mechanical discipline transformed the lessons of near misses into calculated improvements. The point of inversion was the realization that while the V3 was engineered for launch, its operational status depended equally on the return phase. The plan to catch the Super Heavy booster with the Mechazilla tower integrated directly into the mission plan demanded millimeter-level precision at near-terminal velocity. This created a critical vulnerability. Even a 1.6-degree deviation in roll angle during the catch window could shear the vehicle against the steel arms. The insight payoff lay in recognizing a legacy logic within the V3 control systems. Telemetry from pre-launch modeling revealed that the control algorithm still weighted vertical stability more heavily than lateral drift during the final 300 meters of descent. This bias was an artifact inherited from earlier code, which prioritized survival of the booster landing over the precision required for the tower catch. The residual uncertainty in the final moments of the mission concerns the structural load rating of the tower arms. Though reinforced, the tower approaches its modeled limit if the booster deviates more than 1.8 degrees in final alignment, leaving a razor-thin 0.2-degree margin between controlled recovery and structural failure of the catch system. The next stage of the progression moved from hardware limits to human decision logic, revealing a profound structural error not in the rocket, but in the program model that governed the cost of access to orbit. The paradox was the economic collapse of the Space Launch System, SLS, which was built for guaranteed reliability through conservative engineering, yet collapsed under a force it was never designed to resist, a rival capable of flying more, lifting more, and costing less by orders of magnitude. The engineering mechanics of the comparison were stark. SLS massed 2,600 tons and used 4 RS-25D engines and 2 solid rocket boosters to deliver 93.5 tons to low Earth orbit at a cost exceeding $2 billion per launch. Every major component of the SLS was designed to be expendable, meaning no engine flew twice and no hardware returned to teach the program anything new. The governing decision logic of the legacy program was the assumption that high performance must always equal high cost. For half a century, this pattern defined aerospace programs, with the SLS following the tradition of locked specifications and frozen design. This belief system failed when confronted with a competing vehicle built on iteration and the compounding gains of reusability. The environment of the competitive aerospace market delivered its own judgment. The physical logic of reusability collided with the economic logic of expendability. The SLS design could not survive contact with reality because the maintenance and destructive cycles of expendable hardware inevitably devour a program. This created an undeniable cost ratio of roughly 40-to-1 between the two systems. The systemic risk was the inability to learn from failure inherent in expendability. Every Starship flight, even a partial success, expanded operational confidence because the hardware returned with data or could be inspected for flaws. Conversely, every SLS launch destroyed the hardware that could have provided the next lesson, ensuring that the same destructive cycle was repeated without the benefit of iteration. The core moral of the comparison was the triumph of discipline and humility before physics over the inertia of tradition. The V3 design demonstrated that when assumptions remain static, they are overtaken by machines that evolve, forcing a transition that was mechanical, not emotional. The lesson was clear. Aerospace systems that embrace reuse grow stronger. Systems that resist reuse fall behind. This philosophical shift circled back to the mechanical specifics of V3's vulnerability, detailing how scaling created new structural challenges that were not immediately visible. The large tank volume increased the total surface area exposed to uneven temperature fields, which exacerbated internal stress. Asymmetric heating caused measurable deformation near weld seams during earlier flights because a system so large cannot heat evenly. This structural curiosity was further amplified by propellant slosh. As the free surface area inside the large tanks increased, the slosh amplitude rose, which guidance algorithms had to compensate for. This compensation demanded more engine gimbal activity, which in turn increased bending loads on the thrust structure. The partial comprehension of this instability came through a near-miss moment recorded during early testing. Sensors detected a transient pressure drop of only 3 psi in the liquid oxygen tank during high throttle operation. Had the drop continued for another 0.4 seconds, structural buckling might have begun. This transient event revealed the narrow margin between nominal operation and a catastrophic structural failure. The critical inversion revealed that the largest rocket ever built was threatened by a condition so minute it was almost invisible: resonance. A hypothetical failure scenario showed that a slight misalignment in the thrust vector, less than a degree, could create enough lateral force to push the V3 structure towards its limit, where the difference between stability and collapse measured less than 12 millimeters of lateral displacement at the midsection joint. This small lateral movement was enough to initiate a harmonic divergence. The profound insight was that the causal chain of potential collapse did not begin at max Q or at thrust misalignment, but at the initial flawed scaling assumption. The V3 design increased mass faster than stiffness and engine count faster than damping capacity, ensuring that while the numbers worked in isolation, they failed in combination. The system met the mathematical limit of scaling, which forced a redesign of the internal load paths within the vehicle, including the addition of longitudinal stiffeners. The systemic consequence forced immediate policy changes ahead of the 2026 operational launch. Records show SpaceX performed a software patch to eliminate the legacy fallback mode that favored vertical stability, and new control weighting was applied directly to lateral stabilization. The grid fin actuation sequence was also modified, reducing the average correction time by 14% to combat wind-driven rotation, demonstrating a direct engineering response to the identified risk. The final vector of uncertainty remains rooted in the atmosphere itself, an environmental variable no engineer can fully control. The tower catch system has never been tested under full crosswind conditions, and the atmospheric shear models still rely on seasonal averages that may not capture extreme variance. This means the very environment needed for the routine operational cadence of Starship V3 is still subject to unknowns. The mechanical discipline applied to the engines involve not only widening the combustion margin, but also reinforcing the thrust structure beneath the vehicle with cross-braced steel ribs to prevent oscillation under the combined thrust load. This was a direct response to recorded structural loads from earlier flights that had demonstrated how easily the margins broke. A crucial element of the decision logic was the acknowledgement that an earlier mission had suffered pitch oscillation due to a slight synchronization error between engine gimbal commands and flap actuation timing. This cognitive gap was closed in the V3 firmware by introducing a new compensation loop that eliminated delays shorter than 12 milliseconds, a tiny fraction of time that was nevertheless enough to destabilize the ascent profile. The physical reality of the expanded tank volume meant that ullage pressure control became inherently harder. Larger tanks expand more under heat influx, and pressure waves travel through the tank walls when Raptor engines throttle or gimbal. If pressurization control lags by even 100 milliseconds, the tank deforms unevenly. The nature of the systemic risk was that the transition to operational status demanded unbroken execution. Even though the catastrophic failures of the early tests were eliminated, the process of same-day reuse demands millimeter precision, meaning that a single procedural failure in the catch or refurbishment cycle could halt the entire operational cadence. The civilizational layer of the Starship program is its rituality of iteration. Every Raptor ignition refines performance, and every recovery expands operational confidence, creating a feedback loop that destroys old assumptions. This is the necessary discipline that defeats the hubris of declaring a system ready without constant verifiable data. The closure emerges not from triumph, but from the quiet recognition of how close the system had come to hidden instability. Starship V3 represented mastery built on the collapse of earlier designs, but aerospace systems do not forget their past. They carry every variable forward. The ultimate structural integrity of the V3 remains an open cycle, not yet fully closed by test data. New resonance patterns may still emerge as payload mass grows and tank stretching continues. High-thrust combustion changes subtly with each engine iteration, and cryogenic behavior varies with micro-impurities in propellant batches, all of which sit as unknowns within the operational envelope. The lesson delivered by the V3 transition is simple: capacity is not infinite. The rocket can lift 200 tons today, but every additional ton presses the structure into realms where mathematical certainty becomes more conditional. Thrust does not override pressure, and ambition does not override physics. The system obeys only the laws that built the universe, and every assumption must be recalculated in their shadow. The verdict, as always, will not be delivered by mission directors or flight controllers. It will be delivered by pressure, vibration, heat, and the immutable logic of motion, the only judges that matter in aerospace.